All right. Okay, quiet down, everybody. Don't make me turn the lights on and off. Okay, this is Try a Little Randomness. My name is Larry Hastings. This is an introduction to the whole concept of random numbers in computer science. So, let's start at the very basics. What are random numbers? I think we all have a pretty basic idea, a sort of an intrinsic understanding of what a random number is. But, just to be kind of clear for the purposes of instruction, a random number is a number produced on request from a specific range. So random numbers, at least in computer science, are always bounded on both ends. This number cannot be predicted in advance. So random numbers are produced using what's called a non-deterministic process. Determinism means predictable in advance. So the opposite of determinism is non-determinism, or randomness. Tautologically, random numbers are produced using a random process. What use are random numbers? Well, in computer science anyway, we use them for simulations a lot. A particular kind of simulation called a Monte Carlo simulation, where you use a random number generator to simulate the behavior of individual actors in some sort of grand simulation. Like this is used for simulating weather, or physics, like nuclear explosions, or economics, where we have random numbers deciding the behavior of individual actors inside of an economy. There's a particular kind of simulation, games, which are very popular on computers. So like for instance, anything that you'd normally go to a casino to play, you would use random numbers in order to simulate the random behavior of the physical objects that are used in the casino. And then video games, in general, favorite of mine. So like if you were playing Halo and you were shooting at a grunt, the grunt might decide to run away from you, and whether he runs left or right, he might decide that through picking a random number. How do you get yourself a random number? Well, the best way is with an unpredictable physical process. So you might roll a die, flip a coin, spin a wheel, pick a shuffled card, bet on a horse on a track. Basically anything that you might ever bet on in the real world, that's a good way of producing a random number. But this isn't so convenient for computers, so usually what you do for getting random numbers inside of a computer is to sample a noisy signal. And the noisier it is, the better off you are. So there are some examples of where to get this noise, turn into random numbers. There are actually a couple of websites where you can download high-quality random numbers. There's random.org. Random.org creates its random numbers by having a couple of radios tuned to atmospheric static, and they're sampling it through, I think, the audio in port on the computer or something like that. There's an older one called Hotbits. The guy who runs Hotbits actually has a small sample of cesium-137, and he has a Geiger counter hooked up to it, and he's monitoring the blips from that and turning that into nice, pure random numbers. And then back in the 90s, there was this famous thing from SGI. A couple of guys created something called LavaRand, which was a random number generator. It was a webcam pointed at a bunch of lava lamps, and it would use the brightness from each individual pixel to generate these random numbers. These days, actually, many of your computers, depending on how new your laptop is, you may have a random number generator built into your laptop. There's CPU instructions that are genuinely random number generators now. On Intel Ivy Bridge and above, there's an instruction called RDRAND, which I think at its core is basically like a flaky transistor that's sort of wavering between 0 and 1. But they have a whole bunch of microcode on top of it to clean it up and make it a nice random number generator. Now, modern operating systems also have a way of generating nice random numbers. There's something, I know it from Linux, so in Linux it's called the entropy pool. I think it has a different name on Windows. I'm not sure what it's called on the Mac. But the basic idea here is that you have the operating system itself paying attention to what are effectively random events coming in from the outside world. So like for instance, when did the last network packet arrive? When did the user press and release a key, and which key was it? When did they move the mouse, in what direction, and how far, and did they press any of the buttons? And if you have RDRAND, of course, we're going to take that as well. So you take all of these random inputs and you sort of mix them all together, swirl it all around so that nobody can tell where anything came from anymore. And from that, you can produce a nice stream of random numbers. And that's the end of my talk about random numbers. Because most of the time, when computer scientists are talking about random numbers, they don't actually mean random numbers. They mean what are called pseudo-random numbers. So it's To the point where most of the time, if a computer scientist says random number, they actually mean pseudorandom number. I guess people are tired of saying the word pseudo, or they were just brought up wrong. I don't know what the problem is. But for the rest of the talk, I'm going to try and be very clear and always use the term pseudorandom number. If I say random, hopefully I actually meant random. Now, pseudorandom numbers are so much more common than real random numbers. I think this is why. So most of the time when computer scientists deal with random numbers, they're actually dealing with pseudorandom numbers, and the real random numbers are kind of rare. Why is that? Well, there's a whole talk here. You realize you're jumping the gun. So let's talk about pseudorandom numbers. What are pseudorandom numbers? This is going to be a very familiar looking slide. Pseudorandom numbers it's a number produced on request from a specific range, but here's the difference, which mostly cannot be predicted in advance. Not entirely, mostly. And the really important distinction between random and pseudorandom numbers is that pseudorandom numbers are produced using a deterministic process, a non-random process. And it's here, sorry, I have the quote on the next slide, I guess. So this is the critical distinction between pseudorandom and random. A deterministic process producing random numbers. We're going to talk about what that means. So why would you use pseudorandom numbers? In particular, random numbers sound fabulous. Pseudorandom numbers, I don't know what they are. I don't know why I would use them. There are two important things. First, pseudorandom numbers are plentiful. You have an algorithm, you turn the crank, new random numbers come out the bottom. As opposed to these random number processes that I was talking about, like if you're listening to the atmospheric static, or you have this little piece of cesium-137 that's decaying, you're going to be getting random numbers at a certain bit rate, and you may need a lot more random numbers than you have available right now. And so if you need 1,000 times as many random numbers, you may be waiting until next week. Whereas pseudorandom numbers, you can just turn the crank and get all the random numbers you want out of it. So random numbers, pseudorandom numbers are not bit rate limited, they're CPU limited. The other thing is that pseudorandom numbers are repeatable. Like I said, they're deterministic, which means that you can take a random number generated stream of random numbers, and it can be as long as it can be as huge as the day is long, and you can start over and generate the exact same stream again. So it might be useful, for instance, if you're running a simulation, like you've got an economic simulation, and you say, well, you know, most people, they decide to buy a TV if they have this much money, and you say, well, let's tweak the parameters a little bit and see if it changes. So you can run the same simulation over and over and over and just tweak the parameters that are guiding the simulation, and it's one less variable in the simulation if you're using the exact same stream of pseudorandom numbers to run your Monte Carlo. So how do you get yourself a pseudorandom number? You use math, and hopefully the more complicated the math, the better. And it's here, I have this quote, I thought I was on the previous slide. This is a famous quote from one of your distinguished computer scientists here in England, John von Neumann, and he said, anyone who considers arithmetical methods of producing random digits is of course in a state of sin. And what he really means here is that if you're saying you're producing random digits and you're using arithmetic, those aren't really random digits, those are predictable digits. He's really calling for the term pseudorandom here. So there are two important concepts involved with a pseudo-random number generator, which I'm going to start renaming as prng, just otherwise I'd run out of room on the slides. So prng's two important concepts. The first is what's called the seed, and this is really just all the internal state of the pseudo-random number generator. This can be a single number, it can be a whole bunch of memory. It depends on the implementation. The second thing is the period, because, as it turns out, a pseudo-random number generator, it's not a question of if it will repeat, it will always repeat. Let's say, just as an example, what's going on here is, this is what we call the pigeonhole principle. Let's say that we have all the internal state of the pseudo-random number generator is a 32-bit integer. 32-bit integer has 4 billion possible states. If you produce 5 billion random numbers from it, you're going to wind up with 2 times at least where you're going to have the same state. And if you have the same state, then you're going to produce the same random number because it's a predictable process. And at the point that you hit that same state again, you have looped all the way around. Let me illustrate that with big pretty pictures. So let's say that we have this state S. We run our pseudo-random number generator. We produce n, which is our number, and s prime, which is our new state. And we keep going, and we produce numbers and numbers and numbers and numbers and numbers. And eventually we're going to hit a state which is the predecessor state to our original. So that's when we got our period, our loop. Now good PRNGs, they're going to have nice long periods. and they're going to be indistinguishable from noise. And what that means, I'm no good at this math stuff, but there's ways to measure the entropy of a data stream, and noise produces a very high entropy, and a nice pseudorandom number generator produces also very high entropy. Now, the gold standard in pseudorandom number generators these days is called the mersenne twister. It was open source. I think it was released publicly in 1997 by 2 Japanese researchers. It has a period of 2 to the 19,937 minus 1, which is a mersenne prime, which is why it's called the mersenne twister. The seed is this number, 19,937 bytes, which you don't need to initialize the whole thing. You can just give it an integer and the rest of it set to 0. That's what people usually do. Now, this number, 19,937 bytes, that turns into 624 32-bit words. And I point that out just because that's going to be important in another slide or two. So just remember for now, the size of the seed of the mersenne twister is 624 32-bit words. We'll come right back to that. The mersenne twister, the good news is it has been the default implementation of random numbers inside of Python since 2.3. You can use it by importing the random module. That's not the pseudo-random module, that's the random module. Like I said, everybody uses the term random. Now, this is lovely, but this is hardly unique to Python. It's also the default random number generator used in a whole bunch of other languages. It's also the default random number generator used in a bunch of numeric packages. It's also the random number generator used in a bunch of different C libraries. So it's really everywhere, and everybody's using it, and it's not hard to be using the mersenne twister. Now, there's something beyond just standard good PRNGs. There's a new concept in random number theory called a cryptographically secure pseudorandom number generator. Let's say you're doing cryptography and you need to have a one-time pad, which is just like a bunch of random bits that you're going to use to XOR with your data to sort of hide it so that people can't tell what's going on. Or not XOR, but use a better algorithm than that. So you need effectively some number of random digits. Well, if you're using a poor quality pseudorandom number generator, somebody who is trying to figure out your data might be able to attack you by simulating your random number generator and pulling out the random numbers that you were using and guess your key. So you don't want them to be able to guess your key, so you want to use something that's cryptographically secure. But what does that mean? Well, like I said, this is all kind of early days, but as I understand it, there are 2 tests that people currently have for something to declare it as a cryptographically secure PRNG. The first is what's called the next bit test. The idea here is if you have as much previous data as you want output from the PRNG, you cannot predict what the next bit is going to be generated by the PRNG with anything more than 50% accuracy. So in other words, random chance. The other test is what's called the no state compromise extension test. What this is, state compromise extension. So what they're saying is, if the attacker ever gets any piece of the seed, they get part of it or all of it, they cannot take that seed and then run the algorithm backwards to produce what the previous random numbers would have been. The mersenne twister, I believe, fails both of these tests, actually. If you get 624 of inputs out of the mersenne twister, you can reconstruct the internal state, and then you can run it backwards and produce previous numbers. So where we have good PRNG, of course, we have, oh, right, and I had one more thing on this slide, which is the best way we know of to generate a cryptographically secure PRNGs is actually to use existing cryptographic technology. So use an existing known to be secure cipher or hash to produce the random numbers at the end. So where we have good PRNG, we have bad PRNG. Bad PRNG is typified by having a short period and by having hidden patterns, so being distinguishable from noise. Now, what I'm talking about here is that the random numbers aren't really as random as you might have expected. And again, you can measure the entropy of the stream. This can come out in the ways that you're using the random number generator. So like, for instance, let's say that you were using it to run a simulation and you're trying to decide whether people like cats or dogs better. It might turn out that because of your bad random number generator, the people are deciding that they like dogs better, when in fact, if you ran it on real random data, you wouldn't get any sort of correlation. So it's that sort of hidden patterns inside of the random data can emerge outside when you run your simulation. There's another example of this. Again, in computer video gaming, you can exploit AI behavior if you know, if you can control the seed a little bit. I remember watching people, so there's a thing that people do these days, it's called speed runs, where they try and play a video game and get through it as fast as possible. And you're not allowed to use cheats, but you are allowed to exploit bugs or implementation misfeatures. So I remember people were playing a video game on the original Nintendo Entertainment System from the early 80s, and what they did is they powered it off, and they powered it back on and started the game right away. And the reason for that was that the NES didn't have a real-time clock, and so they seeded the random number generator inside with like the number of clock cycles that had run or something like that, or the number of seconds the system had been on. And if they did it right away, then they got a very favorable seed and the game was much easier. So, the bad old style of random number generator, pseudo-random number generator that everybody used to use was called a linear congruent generator. And this is a very simple expression of the form, you take the existing seed and that becomes the random number you return. And then you take that seed, you multiply it by constant, you add another constant to it, and then you throw away the top bits, you just keep the bottom number of bits, whatever it is. This is fast. This has very little code. This is very little data, but again, that's actually kind of a downside because, like I said, the period is constrained by how big the seed is, and here the seed is going to be quite small. It's an integer on the local system, usually 32 bits, maybe 31. It's just kind of a bad random number generator. These were used back in the bad old days when computers were in tens or even in ones of megahertz, and you had, 16 meg of memory or less. There's really no excuse for it today. So back in the bad old days, there was an algorithm called randu. I think it was used on Fortran. I'm really not sure where it comes from. Randu was an LCG of this form. It didn't have an addend. It just had this multiplier constant. And Donald Knuth was quoted famously as saying, "Its very name randu is enough to bring dismay into the eyes and stomachs of many computer scientists." On a similar note, and this is what I find really interesting, so let me talk about Visual Studio. Microsoft ships a compiler for Windows. It's called Microsoft Visual Studio, and it has inside of it different compilers for different languages. They have Visual C#, they have C++, and they have a C compiler, which is distinct from C++. Shipping with the C compiler, of course, is the C runtime library. Inside of the C runtime library is a random number library called rand, I think, or random. It has a function srand to seed and rand to get a random number. Their rand implementation is a linear congruent generator in 2014. It's of this form. They're using at least both the multiplier and the addend. Here's the source code for it. Now that's in C, so I will wave my magic wand and turn it into Python. Well, this is the only Python you get in this talk, unfortunately. So this is not great. And why would they still be shipping this in 2014? I've heard two different theories. One is Visual C just isn't getting a lot of love because their interest is in C# and C++. The other idea is that this is for backwards compatibility because there may be people who are dependent on the behavior of the rand function in the C library, and they have code from 1993, and they still want it to run. I don't know, but I can tell you that this is not the function that you get with glibc. You get a much more intelligent random number generator. So to show you what it looks like when you have a bad random number generator, I did a little bit of visualization stuff. So what I did is I took pure uncut random data from random.org. I took a 256 by 256 image. It was pure white, and I iterated over the data from 0 to 255 across the bottom, and I would take the random number, throw away the top whatever bits, just keep the bottom 8 bits, and make that pixel a little bit darker. So I would use that as the y-coordinate for each x, and I would just iterate over and over and over and over, thousands and thousands of times. And you might expect that to look like a gray field, but actually, it looks kind of like TV static. This is, again, I'm not a mathematician, I'm not so great at this stuff, but random numbers don't tend to be uniform, they tend to sort of clump together. This is something called the Poisson distribution. So, properly, this is correct. This looks like, this is what random numbers look like when you follow this algorithm. So that's pure random data. If we do that with the mersenne twister, again, it also looks like random data. If I take the Visual C random function, now it looks a little nastier. So you see these long streaks. What's going on here is that, like around here, let's say, this is the really bad one. You see there are a lot of black spots, really dark spots, and a lot of white ranges. What it's telling you is every time through the loop, you're never going to hit one of these white spots. You're always going to get a number that's going to hit on one of these black spots. So there is a hidden pattern in the data. An even better example of this, I love this picture. So the reason I talked about randu in the first place was because of this visualization for randu. So what they did is they took a 3D space and they took triples from randu from 0 to 1, normalized, and they plotted those. And it looks like this. This is called, they call this the 15 hyperplanes of randu. And what this is telling you is you take those triples, it'll never, ever, 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 ever fall in one of these white gaps. It's always going to fall in these black 15 hyperplanes. So, to sum up, random numbers are genuinely random. You get them in computers from a noisy signal, but they're limited by bitrate and they're kind of rare in real computer science. So most of the time we're using what are called pseudo-random numbers, which are much more plentiful. They are produced using a deterministic process. You have the concepts called the seed and the period. There's bad PRNG, there's good PRNG, and even better, there's cryptographically secure PRNG. And finally, you should just use the mersenne twister, which is what everybody does. Thanks very much. I'm bang on 20 minutes, so I have time for questions. Oh, good. Van, I'm glad that you held to the tradition of falling asleep during my talks.
That's working.
So how can I find a gambling address?
Yes, let me get you the bar. We've got a microphone headed your way.
So how can I find a gambling application that uses that third?
I would say find a really old one. Load up, get one of those old VAX simulators and run VAX, and then use like the cribbage game that shipped in user bin games or something like that. Yeah, anything that's really old and cranky like that. You don't want anything compiled recently because that's going to use the better random number generator that's in glibc these days. Anybody else? Oh, Harry?
Hello. Excellent talk.
Thank you.
Maybe I missed this, but can you combine the two somehow? And
Yes. Well, the traditional thing, I guess I should mention this actually. So what people used to do is they would seed their pseudo-random number generator with something that was hopefully a really random number. So like for instance, they would seed it with the current time on the real-time clock, which I kind of alluded to when I was talking about the NES. Seeding with the current time, bad idea. Seeding with your IP address, also bad idea. Seeding with the current time, XORed with the current IP address, still a bad idea. The best thing to do, let the mersenne twister seed itself if you don't care about the seed. If you do care about the seed, then you already know what it's going to be anyway. So the mersenne twister will self-initialize with something, I don't know what it uses, but it's something relatively reasonable. And if you want to be really secure about it, like I said, most operating systems now have this entropy pool, and they may have RDRAND. So they're going to have a source of very high-quality random data. You take just a little bit of that and use that as your seed, and now you can produce lots of random data that nobody could predict in advance.
Right, let's just do that then. That sounds good. Let's do that for everything.
Okay. All right. It may very well be what the mersenne twister does.
We solved it.
You mentioned that the new Intel CPUs come with the entropy for the flaky transistor.
I think so.
Why does it do that?
Why does it do that? That's a noise. Having those, it's just a theory. I don't know how it actually works internally, but the flaky transistor, that's going to be unreliable. So it's like reading flaky RAM. You don't know whether it's 1 or 0. Well, that's good. That's random. We can't predict it in advance. So it's a source of a noisy signal, and it lives on the CPU. You don't even need any external processes. So I think it's a good idea.
What's the point?
What's the point? It's to produce real, genuinely random numbers for applications that need genuinely random numbers, which turns out they still have a use in this modern society where we have lovely PRNGs and the mersenne twister.
Did you mention crypto as an application?
Again, as a sideline, yes, when I was talking about cryptographically secure PRNGs, you need it for your one-time pad.
Right.
But thank you for checking my homework. Okay. Class dismissed.